Welcome back to the module on applications of probabilities. As I promised you in the last lecture, we're now switching gears towards applications in the courtroom. A famous problem in legal issues is the so-called prosecutor's fallacies. At the very basic, it's a mistake in logical thinking. And in particular, in our language, in probability, it's a confusion between the probability of A given B versus the probability of B given A. Essentially, the question is what has happened already and what's still uncertain. Remember, probability of A given B means condition B holds. What's the probability of A happening? A is still uncertain. B has happened. While in the other way around, probability of B given A, we know A has happened, A is known, but B is still out there, is uncertain. What's the probability of B happening? And this difference can lead to terrible misjudgments. There's a whole legal history now on issues or on cases where this got screwed up. In particular, it's important in the evaluation of evidence, for example, in DNA comparisons among possible culprits in a crime. First, I want to explain to you the problem in sort of our language of probability and conditional probabilities, and then we're going to look at an example from legal history. Here's the question. We have a defendant in court. Is he or she innocent? So the event I says the defendant is innocent. The opposite, I complement, is guilty. So let's just look at innocent versus guilt. Nothing in between. So don't tell me, oh, I smoked but didn't inhale. No, that doesn't exist here. Innocent versus not innocent. I complement. And then there's the issue of what I call the DE, the damning evidence, the really bad evidence that we have and why we're in court. This could, for example, be the DNA match at the crime scene. Now let's look in our language, what do the two different conditional probabilities mean? First, the probability of the damning evidence given the person is innocent. So that's a probability that an innocent person, so that's what we assume, we know person is innocent, matches the damning evidence. Whether he or she matches the damning evidence, that's now the uncertain part, that's where we still have a probability. Now let's think about it the other way around. What's the probability of I given DE? The probability of being innocent giving the damning evidence. That now means we have a person who has the damning evidence, maybe his or her DNA matches something found at the crime scene. So DE has happened, and now the question is this person innocent or guilty? So that's still out there. Notice the difference between those two probabilities. Here's now the heart of the problem. You go to court. A prosecution's expert witness says an innocent person has a 1 in 100,000 chance of matching the damning evidence. And now comes the prosecutor's fallacy. Now the prosecutor says, the defendant has the damning evidence. Therefore, there's only a 1 in 100,000 chance that the defendant is innocent. Clearly is guilty. Jury, judge, I say the defendant is guilty. Send him to prison or her to prison. That's the prosecutor's fallacy, and this thinking is wrong. Let's look at what the expert witness said. The expert witness said the probability of an innocent person, that the person is innocent, has the damning evidence is 1 in 100,000. The prosecutor's fallacy is now to turn this around and say, the damning evidence match is there. That's why now the probability of innocence is also 1 in 100,000. But that's wrong, because in that argument, the prosecutor changed the uncertain statement, that's still uncertain, and the condition around. But those two probabilities are usually different. Now you say, oh, that's a problem. How do we get the other probability? We have Bayes' rule. Do you remember Bayes' rule from this flipping probabilities in the previous model? We actually have at least a theoretical way to go from the expert witness's statement to the probability that the prosecutor, the jury, and the judge care about. Remember the flipping formula. The probability of I given damning evidence equals the probability of damning evidence given I times these two other probabilities, or this ratio of two other probabilities. Now, the question is, what is the probability on the left-hand side? That's really the one. We have found damning evidence against someone, but what's the probability that this person could still be innocent? Or the probability that this person is guilty? On the right-hand side, we have the first probability. That's what the expert witness says. That's a tiny, tiny probability. But wait a minute. This now gets multiplied by a ratio. If that probability of DE is very small, we're dividing by a number that's very small. And a small number divided by another small number can suddenly get a little larger. Let me illustrate this in a simple example. The guilty person is among 500,000 people living in a town. Let's say we know this. Because of circumstantial evidence or timing, someone was robbed or murdered or something. We know, we are down to 500,000 people, and let's make the following assumption. The guilty person left some DNA, or there's some match that that the guilty person also has, and that's our damning evidence. So, here now probabilities we know. And so simplification, let's assume there's a single culprit. There's only one criminal. We don't have a group of criminals that did this somehow together. So there's a single person that's guilty and the rest is innocent. So that gives me the probability of being innocent and the probability of guilty. As you see here, 499,999 out of 500,000. Those are all innocent and that last person is the guilty one. And we know if you're the guilty person, if IC is true, the complement of innocent, IC the guilt, then the probability of showing this damning evidence is 1. Using these probabilities, I can now use Bayes' rule. I can calculate the probability of the damning evidence, and I can calculate the probability of being innocent, giving the damning evidence, and being guilty, given the damning evidence, and you have the probabilities here. So there's a 1 in 6 chance that given the damning evidence has been found, the person is guilty, and there's a 5 in 6 chance that the person is innocent. The calculations are here, you can look at them. So look at this. We find the damning evidence for a person. The probability that he or she is still innocent is 5 in 6. What's the logic here? How can that be? Here's another way of looking at it. Given the probabilities that we have, so we have 500,000 people, and the probability is of any innocent person having this damning evidence here at the first calculation is 1 in 100,000. So let's do simple math. You have 500,000 people and a 1 in 100,000 chance that an innocent person has that same DNA or the same sort of soccer shoe or something that was found at the crime scene. 500,000 people. 1 in 100,000 chance of someone by accident having this. That means in that city you have 5 innocent people who match that stuff, plus a guilty person. That's 6 people who match them. One of those 6 is a bad guy, the other 5 are the unlucky guys. So that's now the idea here, is that because the chance that an innocent person has this damning evidence, even if it's small, if the number is large enough of potential criminals and therefore also potential innocent people, that's how we get in the end quite a large group, in this case 6 potential criminals, but only 1 did it. And so even if you have that wrong DNA, yeah, there's still a good chance you're innocent. And that's sort of the intuitive explanation here, that for some of you may be a little easier than just going through the tedious math of applying Bayes' rule. And here I sort of summarize this in a probability table. Perhaps this is a little more familiar for some of you now that we have worked with probability tables. That sort of summarizes all the probabilities. Now, you may think this is kind of obscure and never happens. Sorry, no, that's not the case. If you Google prosecutors' fallacies, you will see many, many examples. I picked out one that's sort of well known now in legal history, a famous one, and that's this group of the so-called Birmingham Six. So, let me tell you a little story. Remember, back in the 70s, there was still a lot of or many issues in the United Kingdom between the Protestants and the Catholics in Ireland and Northern Ireland. And there was a terrorist organization called the IRA that organized bombings and killed British people. And in particular, a bad crime happened in the second largest city of England, Birmingham, in November of 74. There was a bad pub bombing where 21 people were killed and 182 were injured. Quickly, 6 men were found who became infamous as the Birmingham Six in the UK press. And they were found guilty of this murder less than a year later, in the August of 1975, and each defendant received 21 life sentences. The key statement why these people were found guilty is the following. A forensic scientist had said that among these 6 defendants, they all had to do tests, and he was sure up to 99% that 2 out of these 6 Birmingham 6 people had handled explosives. So here was his claim in our language. The probability of handling explosive, given that the test, his special test is positive, is 0.99. And people said that's so high, clearly these bad guys handled the explosives and they must be the terrible criminals. Now, it's not 100%, it's only 99%, and because these tests are not correct. In particular, at the time, it was known that other substances produce positive test result, including nitrocellulose. I don't know whether I pronounce this correctly. This chemical is present in paint, on playing cards, in gasoline, cigarettes, and soap. Now, here's the problem of what happened. The expert witness already made the prosecutor's fallacy, because what he should have said is the following. If you handle explosives, then the test will be positive. So, then you'll come in touch with this chemical and the test will give us a positive signal. But the claim that he made, if the test is positive, that means you handled explosives, seems to be much smaller. Then many of us on any given day get in touch with gasoline if you go to a gas station. For smokers among you, you may get in touch with this if you smoke. If it's in soap, well, many of us get in touch with that. And other reasons. In particular, the defendants had been caught on a train playing cards. So what happened eventually? After various appeals, finally in 1999 there was a second appeal and they were all released from prison. And actually nowadays people think that these people were actually innocent and that other people, and apparently there's some known names, but these people didn't get convicted for doing the crimes. There were other issues at these various appeals and at these various trials, but at the very heart was this misstatement from the forensic expert who had already done the flipping that he shouldn't have done of the conditional probabilities, and he committed the prosecutor's fallacy. And this is just one famous example of many others in the legal history where people confuse what's given, what have we found, and what's still out there. And what we have found is the evidence or the test result. What's unclear is the innocence or guilt. But people often then argue with it the other way around. Whenever we have a prosecutor's fallacy, that's a neglected application of Bayes' rule. People are forgetting about that they really should use Bayes' rule. Next, and as our last application, in the next lecture, I will show you a particularly sad story of a real tragedy where the prosecutor's fallacy led to a lot of harm. So please come back for the last application of this module. Thank you.